All right, lesson set 43, problems 41 to 63, and get some practice in. Name that tune. Well, I hope you're seeing a negative absolute value. Starting with -4, I'm going to make it act like a 0 because that's the shortest distance you can travel is 0. And I want a 2, and I got the marker full of ink, so I can write the number 2. And how do I get from 2 to 1? I go down 1, and it's why it's negative. And -4 to 0, up 4, but it's really the absolute value of 4 because I'm canceling absolute value units. And there's that tune. A to the -2, commonly called 1 over a squared. Well, I guess that tells me that if that's in the numerator, I can move it as a positive expression in the denominator. Now, what if I was dividing by a negative? What if I was dividing by a to the -2? Well, that's the same thing as dividing by this. And that means I'm going to multiply by the reciprocal. So I'm going to actually show multiplication with x. I don't want you to confuse that with a variable. So I'm multiplying by a to the 2 over 1. So what do I learn? I learn that if I have b to the -2 in the denominator, well, that's the same thing as 1 over b squared in the denominator. And that's the same thing as dividing by 1 over b squared, which means I can multiply by b squared over 1. And what used to be a negative in the denominator is now a positive in the numerator. So I'm always going to move negative exponents into the other location. If I got a negative exponent in the numerator, I'm going to express it as a positive in the denominator and vice versa. I see a negative. Well, first 12/10 is 6/5. Right now, let's move the a to the -2 here. I'm going to leave a to the 4 there. I'm going to express things with positive exponents. B to the -2 means I've got b squared there. B to the -4 means I've got b to the 4 here. So what's my final reduction? 6/5. Now I've got a's, but it appears as though I've got 6 in the denominator. And it appears that I have 2 more. B squared times b squared. Right? And how many times does b squared go into b squared? Doesn't cancel. It actually gives me the value 1, but now it disappears. There's your answer to that problem. Feel free to do it again. 32 to the -4/5. Well, I'm going to do the 5th root of 32 first. That's 2. So I've used that. I still have -3. Well, I hope we know that that's 1 over 8. 1 over 2 cubed. This stage, I think most of you know it. This is √3 times √3 times √7. That's how I'm expressing root 21. We've looked at earlier lesson sets as to why I can do that. So I'm not going to get into that, but I am going to draw the picture one more time. That's 3 by definition. That's its square root. And a number times itself, right? Squaring, I think I'm taking that and I think I'm squaring it. Squaring it. Yeah, I hope you see this is equal to 3√7. This is all about exponential activity on top of m. Well, I got base m. Why don't I look at the exponential activity? And if I do, I think I got 36 here. Let's see why. Well, I can move the -5 into the denominator. There's a 1 there, though. That gives me 1 over m to the 12. 1 over m to the 12 is the same thing as m to the -12. That times that is 36. I think I found the exponential activity on top of m because these are inverse operations. What's your answer? All right, let's see. Don't have Rene Descartes here. Heavy desks, but I gotta have to move it. I hope that's far enough to capture the next problem. It's not quite. Yeah, I guess I'm good. That's the last problem. Yeah, that's the last problem. All right, so domain and range. Oh, it would be nice if you knew what that graph looked like. It's got an x value of 1, and it's going down. Put some numbers in, you'll find out that trajectory is true. You want to understand algebra, work with the numbers. All right, -1, excuse me, talking to you rather than looking at it closely enough. All right, so this starts at -1. And it looks like I don't have any x values over here that are giving me out y values. I don't see any. But I do see these x values. Yeah, they're giving me these y values. Yeah, I guess I can use these. Question is, how do I describe that going in that direction? Well, I hope you say domain x values greater than or equal to -1. That's what I see. And the range, if I put -1 in, then I get an altitude of 4. Then I guess I'm asking, what are all these altitudes? Sure look like they're below 4. Range. Started a conversation here. Sketch, well, I know it's cup shape up. I know -8x plus 1 is a tangent. It's going to be on this side because that's where I'm going decreasing. So that's going to get me a 0, 1. That means my x value has to be positive. 8 divided by 4 is 2. I just did minus b over 2a in my head. But I didn't have to even worry about the minus sign because I knew it was positive. So what's the opposite of -8? Positive 8. 2 times 2 is 4. You drop a 2 in, you got -16. You cut that in half and add 1. -7. I guess I got the sketch. Enough said. You get the point? Aha, that was a joke. You get the point. I'm sorry. I apologize. 3, 4. Over 4, up 3. That looks about right. And I have graphed using what? Point and slope. Guess what this is called? The point slope form of a line. I see cup shape down. Why am I doing this again? Oh, that was a name that tune over there. Okay, now we're going to name it a different way. Looks like a 4 gets you a 5. That means 0's over here. I always like the y-intercept. -12 plus 5 minus 7. I guess we're done. 4x. 4x. Textbooks commonly call this a term. That's a term. Well, I want you to know that that term is also a product. What's 7 times 93.8924, 69, 74, 200, 1,000, whatever? I don't know. What's 79.4321 times 0? I know the answer to that. So I think every product deserves a 0. Can you figure out what times -6 gets you 24? That's a point on a line. That's a product. I'll make that equal 0. Looks like that's 6. We'll call this A, we'll call this B. B's over here. A's over here. Looks like I got the graph. This is called standard form, and I use the x and the y-intercepts. And if you don't use the x and y-intercepts, and we've been doing it that way for the entire semester, gotta wonder why. The inverse, is that what oh no, this is working with derivative. I thought I was looking at that. So I've actually given you a derivative. And to understand that, you got to look at the videos that built you up to that moment. And a lot of you haven't. So this is going to be a little meaningless for a lot of you, but I got a few students who have looked at it. All right, so these are the table values I've been putting on lesson sets for quite a while. And I hope you can see the 2 to 1. When x is 1, it's going up at 2 to 1. When x is 2, it's going up at 4 to 1. When x is 3, it's going up at 6 to 1. It looks like x squared is going up at a rate of 2x. And I'm going to multiply that by 3 because I'm going to triple that. That's a constant rate of change. And now I have a formula that tells me the rate at any instant. At any instant on that function, I'll tell you how the table values are changing. Kind of proved it here, I think. And I know that that's a cup shape up, and I know it's flat right there. It's not changing much at 0. Yeah, we talked about y in other videos, but it's not changing much. So I guess I want to know when that's equal to 0. I guess that gets me a 2. And what have we done to get that x value? Minus b over 2a minus b over 2a. Boom, get the same answer. Wow. And I've been telling you that you've been going down at 12 to 1 on something like this. Well, what happens when you plug a 0 in here? 0's over here. That's on the downside. You're actually at 0 going down at 12 to 1. And every friendly number, we put a 1 in, you're going down at 6 to 1. That would have been here. And if you put a 2 in, you're going down at 0 to 1. Yep, that's 2 jumps from 0 to 2. Okay. Said what I had to say. Now I got to move this table again. Here we go. Wish I had Rene Descartes. Ooh, wish I had Rene Descartes. All right. Sine of 19 pi over 3. We're starting to get there. It's been 3 days of practice. And a lot of you are doing that right today, class. Yay. Multiples of 3. I'm seeing 18 pi over 3 as the closest multiple. I think that's 6 pi, which I think is over here. I think it's 3 revolutions. And I want to get to 19. I think I need 1 more. I think that's my triangle. I think that's a half. I think that's root 3 over 2, and I think that's 1, and I think I'm looking for the sine. I think I'm looking at root 3 over 2, which is approximately 0.87. I hope all of the camera captured that pretty high on the board. Yeah, we got away with it. All right, so we're making gains there. We want the period of this function. Well, heights start in the middle and go up to 1. So my function does this, 1 period, and I know that that distance from there to there, that distance, d, is equal to pi over 6. Because theta is just a Greek letter, stands for an angle. You can write x, doesn't matter. 12, so if this is going around the circle at a normal pace, then that would be 6.28 units around the circle. But what if I'm going 12 times as fast? Ready? 12 times as fast as that. Whoa, boom, I'm done. Well, isn't that going to make it do this? I'm going to get all those numbers between 1 and -1 much more quickly. All right, so to get the period, all you have to do is take the multiplier and divide it into 2 pi, or if you prefer 360, divide by 12. That's 30 degrees. And if I have 30 degrees, then we've been drawing the circle. 30 degrees is chunks of 6, right? Well, how many chunks do you see? I see 12. So if I do 30 degrees worth of circumference change, and then multiply it by 12, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, I got 12 of these distances. Well, that distance is your x-axis, really. That is your x-axis. And so I'm going 1/12 of that to get 1 rotation. Now, you're going to have to hear that quite often till that makes sense to you. But let me just graph this. All right, where can I graph it easily? I guess I can graph it over here. Let me get some room. All right, so we've established the period of the sine function. First 90 degrees, it goes up from the middle. So I'm going to do that, up from the middle. All right, I know the sine function starts at 0, right there. Okay, so I'm looking at making 12x equals 0. That's the argument. This is what dictates angles right here. This is all about angles, creating ratios between 1 and -1. All right, so I set it to 0. That's easy to see. I start at 0. I guess I should put in the midline, the range here, right? You're all pretty good at that now. We've talked about that enough. And that's 15, right? Right, because the sine function only kicks out numbers between 1 and -1. The If I multiply that by 5 and that add 20, I hope you're starting to see the range. And then I set 12x, the argument of the function, to 360. If it's in degrees, which I'm not in degrees, 0 is radians, which is radius lengths, right? I hope you can see C is 2 pi r, and we're working with a unit circle of 1. So once around is 6.28 units. It's useful for you to know some numbers, 0, 1.57 radius lengths. In other words, whatever that radius length is, if I multiply it by 1.57, I've roughly traveled that far, 90 degrees. 3.14, 4.71, 6.28. It's good to get familiar with those. It's going to help you when you dive into this more deeply at the next level. Just trying to get you started so you get off to a good start. All right, so when does 12x equal 360? 30 degrees, but we're solving this. So that's going to be x equals 2 pi over 12, which is pi over 6, and that means pi over 6 gets me back to 20. Now I got a lot of symmetry here, and I can find a lot of other values with symmetry. All right, tangent is 79 pi over 4. What's the closest multiple of 4? 80. 80 pi over 4 is 20 pi, even is on this side. But instead of a 45, 45, well, it doesn't matter, right? 45, 45, it's just as easy to keep the fractions. Root 2 over 2, root 2 over 2. First quadrant, your x and y are both positive. That's your x, that's your y. That's your x, that's your y. They're both positive, so it equals 1. Wait a minute. I did 79 pi over 4. I just got tired on a Friday afternoon. I should have been here. Got to do it again. I'm 1 less. I just did 1 more. It happens. I should have been here. And the reason I picked that one was I wanted to make sure you put a negative on that one. So what was my answer? It wasn't positive 1. Should have been negative 1. I'm not going to redo the video on a mistake like that because it's the end of the Friday and I'm ready to kind of move on. Oh, I am moving on. Hey. Yeah, tomorrow morning I'll come in and do another 20 problems or finish the lesson set. Right now, we're just going to get up to problem 63. All right, so sine function. In the unit circle, no, I didn't do that too well. I'll do it here and then erase it. In the unit circle, if I have an angle, just an angle, then this is the sine of that angle, and this is the cosine of that angle. As far as I'm concerned, that is a height, providing I've got a hypotenuse of 1. And this is a width. I see the sine function as a height. So I'm really solving 2h minus root 3 equals 0. But what do you have to learn? You got to tell me what that stands for. And I just said it 5 minutes ago. The question is, did you hear it and do you remember it? What do we do in trig? I give you an angle, you give me a ratio. If I give you a ratio, you're going to learn to give me an angle, but we haven't talked about that yet. I did talk about it with a couple of students in class, but not many. So I think h equals root 3 over 2, which is a familiar ratio. Are you practiced enough to know where on the circle you get that? Well, the sine function has a maximum height of 1 and a minimum of -1, and heights are 0 in the middle. And I asked you to memorize that as a decimal, 0.87. I think I'm around here and around here. Does that look familiar? Does that look familiar? I hope so. I hope you see that as a 60-degree angle and this as a 120-degree angle. Gets me root 3 over 2, positive 0.87, positive 0.87. Yep. Okie dokie. Cosine and negative 5 pi, because these are always, I always write this for these problems, 2 pi, right? That means the unit circle. Okay, I want your answers to be angles between 0 and 2 pi. And I know it's easier for you still to hear 0 to 360, but we're not going to work with degrees much. Not if we're out in the field with the old surveying equipment. Minus 5 pi over 6. Can you do it in your head? I think so. I think I'm looking at minus root 3 over 2, but let's find out with a drawing. Good drawings get good answers. Minus pi over 6 is the bottom half of the circle, broken up into 6 parts. I want to count minus 1, minus 2, minus 3, minus 3 pi over 6, yes. Minus 90 degrees. Should have been straight up and down. Off to the side here, minus 4, minus 5, right here. Well, there's my triangle. I think that height is below the x-axis. I think that's minus 1/2, but I'm not looking for the sine. No, I'm not looking for that. I'm looking for this width. And I know I'm centered at 0. Does it look like it maybe is minus 0.87? If all the way over here is -1, I'm missing some width here, right? Hope that's believable. Hoping that, a lot of these problems you're starting to put in your pocket. And we hopefully do them enough every day that they stay in your pocket. WX, I guess we're graphing this. All right, so let's get a quick graph. All right, it's a negative cosine, so boompity. That's how I'm going to graph that. This is going to be 6, this is going to be 16, this is going to be minus 4. All right, that's there. What makes a 0? 4 gets me -4. What makes 2 pi? Well, let's get the period first, because I can always measure this from 4 plus the period. Right? I mean, that's really that distance. That distance is what I'm adding to 4. So I know that number already. We'll see it materialize here, but I also know it's 2 pi over 3 just by looking at it. I know I'm going to get that. So where did that come from? Setting 3x minus 12 to the end of the revolution, 2 pi. Well, that's the same thing as 3x equals 12 plus 2 pi. And if I divide by 3, I get 4 plus 2 pi over 3. Now, 2 pi over 3 is 120 degrees. What happens to you if you multiply 3 times 120? Once around the circle, go Che. 1 revolution. Point of inflection. Let's get this out of the way. Point of inflection. And the rate at the point of inflection, well, we might as well graph the thing. So the point of inflection is minus b over 3a. Do you remember why? The average of the roots. So let's find the rate at this instant, because I don't know how to draw it until I know the rate. Well, I got to find h. H is the point of inflection. So I got to do minus b over 3a, which is positive 6 divided by 6 is 1. Well, that's easy. 2 minus 6 minus 4 plus 2 minus 2 plus 5, 3. So I now know the point of inflection is 1 comma 3. I got to find the rate. The rate is c. 2 minus 3 times a. A is 2. H was 1. And I got to square that. Oh, I'm going down at 4 to 1. Okay, so I'm ready to draw this. All right, there I am going down at 4 to 1. And I know I'm going up at 2 to 1 at the y-intercept. So this is 0, 5. So I know I have a local max here. All right, and I know what it is already. I'm measuring from 1. So I'm going to say that x value is measured from 1. Looks like I'm going this way to get there. So I'm going to write a minus sign. And it has everything to do with this rate. The opposite of that rate divided by 3 times a. And that number, my friends, is less than square root of 2/3 is bigger than 0. Right? But it's less than 1. So I'm not going all the way over to 0. I'm going part way. And then this one over here would be 1 plus the square root of 2/3. That would be that x value. What the y is, I don't know. I don't want to put that through that. Please don't make me do that. I don't want to. Well, but that's that. All right, now I've written out a word problem, but I don't feel like writing the words out right now. So you give me the words. How do you say that? I hope you say y varies directly as x. And this is the constant of proportionality. We got to find that. I got some help. I know a 7 gets me 21. I think that's a 3. So I think I know what to multiply by in order to get 9. Yep, that got smaller and that got smaller. Direct change. And then I gave you this one, I guess. And I'm hoping you know how to read that. Y varies inversely as x. So if y is 5 and x is 10, then I guess this has to be 50. Because 50 divided by 5 is 10. That's always the first step. And then what? Plug in 6. You'll get your y, which is 25 over 3. This number just got bigger. Bigger. This number got smaller. That's an inverse relationship. And I wonder if you can read this. Y varies directly as the square root of x and inversely as z squared. Or y varies jointly as the square root of x and inversely as z squared. Last problem, then I'll upload this, call it a day, come back tomorrow morning. I'll do problem 63 to 113. 2 chunks of 20. It's 20 and a 30. 20, organically, and then the rules of logs. The rules of logs are going to be 2 ln of 2 plus ln of 5. That's the same thing as that. This is an exact answer. This is 2 times 0.7 plus 1.6, 1.4, 1.6. It's about 3. So e to the 3 is really close to 20. Yeah, if you do this 2.71 3 times, you're pretty close to 20. But the bigger this number, the more inaccurate we get. A little change in x on an exponential, big change in y. Big error. But locally, to help us learn the rules of logs, now it's time to see where that came from, and that's where you got to put your thinking cap on. All right, so 20 is equal to 4 times 5. We know e to the 0.7 is approximately 2, and e to the 1.1 is approximately 3 from our earlier lesson sets. So I'm going to write 4 as 2 squared times 5, and I'm going to write 5 this time as e to the 1.6. Why did I say 3 here? All right, that's another one. E to the 1.6 is approximately 5. I should have put that one down. But, as I said, it's Friday afternoon. Done a lot of math already today. Getting a little tired. All right, so that is another way of writing the number 5. 2 is e to the 0.7. All right, it's time to see the exponents. What do you do when you have something like m to the 6 times m to the 2? I think you add. When you multiply the quantities, I think you add the exponents. I'm adding these exponents. This is equal to m to the 2 plus 6. All right. And I got a multiplication. So I'm going to add this exponential activity. What do you do here? You multiply. And I'm multiplying 2 times 0.7. So this could have been written as the ln of 4, which is the ln of 2 squared. And what I'm saying is that's the same thing as this, and I hope you can see it. Gonna keep doing that till you can see it. And if you can see it, you're way ahead of the game, way ahead of the game. For most people, it's just to do this, get that. And I did that in high school. I got an A. I had the ln of A plus the ln of B. And I wrote the ln of AB. And I got a check. I was so happy. I remember it. Did I have any knowledge of the natural logarithm? Absolutely none. So was I accomplishing anything with that? Absolutely not. Except I remember it. Okay, so I did remember a rule. I just didn't know anything about what I was dealing with. I think you need to know some numbers. Okay, I think every function that we work with, you've got to get a feeling for them by using some numbers and seeing the trajectories and plugging numbers in. That's what you do with x values. So if you're not plugging numbers in for x, I wish you would. All right, done with that. I'm going to upload it immediately. Immediately, kind of like rate of change at an instant. And here comes the instant right now.